So in degree of vertex X, there are 2 of these edges coming into it. So that means our in degree is 2. And our out degree, there are also 2 coming out of it because there are kind of like 4 edges associated with X. So obviously you want your in degree and out degree to kind of add up to the amount of edges that are there. I don't think I mentioned that the other day. And then for Y, there's nothing coming into Y, but there's 1 edge going out of Y. So you have an in degree of 0 and an out degree of 1. Questions, concerns on that one before I go to okie dokie. So in binary search trees, let me try to leave that in there. So remember, we're going to use these in the order that they're given. So the first thing we need to put on the tree is dog, and then we have to kind of compare everything to that. So green, oh, do I know my alphabet? A, B, C, D, E, F, G. It comes after dog, so it goes to the right. And remember, you kind of always have to start from the top. So if I want to put I on this tree, it has to go to the right, but then it's also to the right of green. I'm like questioning my alphabetical ability here. 7 is also essentially going to go to the right of I also. I have a very long direction in that way. Then I get to if. So dog goes to the right of dog, goes to the right of green, goes to the right of I, but to the left of 7. Because it comes before 7 and there we go, the alphabet. 10 is we're going to have a very long. Okay, so 10 goes to the right of dog, to the right of green, to the right of I, Q, R, S, T, but then also to the right of 7. And then finally, cat is something that actually goes to the left of dog. So very kind of right-heavy binary search tree, but kind of depends on your first element, kind of which way is it going to fall heavier to. Yeah. So there's a question on Teams. I don't want to, well, how much smaller does it make the screen? Oh, it actually doesn't make the screen any smaller, just shifts it over. Okay, well then I'll have it up there. So why do some words go to the right and some go on the left? So essentially you're always starting from the top and then you're comparing it. When it comes to words, does the word come before the word or after the word in, a dictionary, if you will? So when I compare green to dog, since G is after D in the alphabet, it would come after dog, so that goes to the right. And then any word that comes before that word in the alphabet goes to the left. So that's why cat went to the left. Whereas like if I was looking at if again, so if was after 7. When you're working with words, yeah, I'm pretty sure it's 100% always alphabetical. I guess they could try to give you some weird thing, but I don't know what they would. I'm going to go with it's always going to be alphabetical because I don't know how else they'd be able to have you break that up. But say I wanted to look at if again. So if comes after 7. So if I was looking at if, well, if comes after dog in the alphabet. So then I have to compare it to green. Well, it's also after green in the alphabet. So I come down to this I. Now this would also come after I. So it goes down this way. And then I compare it to 7. But if comes before 7 in the alphabet, so it has to go to the left. So you kind of, since we have to write these down in the order that we're given, they don't necessarily come out to be purely in alphabetical order, if you will, because, well, maybe it looks like, I don't know what I'm trying to say. But you always have to go down to kind of the end of the tree and then make your new leaf, if you will. I don't think I defined the word leaf, but that's kind of each of the little bottom pieces of the tree are called the leaves. But that's why it goes to the right or to the left. And yes, unless it's numbers, then that would be by numerical order. But yeah, it's either alphabetical or numerical order. Go to the right if it's, greater than or later than that thing in the alphabet. And you go to the left if it's before that thing or less than that thing, depending on whether you're talking about words or numbers. Any more questions on about, my words aren't working. Any more questions about binary search trees or the warm-up in general. There's one word and one letter binary search tree on your quiz. But it's the same type of idea, just with numbers instead of letters. All right. So we started barely 3-1 the other day. Talked about it for about a hot second. Where is it? There it is. And now I gotta do this, and I gotta zoom in. So just to remind us of what this is going to be working on. So essentially we're talking about these things called recurrence relations, and essentially these are going to be kind of functions and equations that kind of depend on itself, if you will. So we kind of had this idea of, you know, you work every day and you get twice as much as you made before. So you kind of had to know how much you made the day before to know how much you're going to make that day. And we went through kind of that idea. And so there's this idea of the original thing that you're going to start with. That's going to be called the base case. And then essentially all of the other values depend on the one before it. So we always do have to have kind of one that's set in stone, because if we don't have that one that's set in stone, then we can't go to the next one. But as long as we have that one that's starting us off, we can kind of go from there. So this is giving us this idea of this recurrence relation. So a lot of them are going to look like this type of, I forgot to put my pen on. Make it draw things. So the equations are going to look like this. This is called a piecewise function, if you haven't seen those before in your life, where essentially it's just defined for different things. So if n is 1, that it's set to be a certain thing, and then from that, it builds upon itself. So that's kind of where we got to last time, is we just kind of built up this idea of what a recursive relation is going to look like. So let's see another example of this really quick. Down we go. So let's say some lady, Susan, signs up with a company for a starting salary of $35,000, and she's promised a 7% raise at the end of each year that she's with the company. And we want to find a recurrence relation to model Susan's salary after n years. What will Susan's salary be at the end of 5 years with the company? Now, the one thing about these, oh, maybe I shouldn't say this. I'll say it. With these, you kind of have a choice about where you want to start. Like this one starts with n being 0. I could technically start wherever I want, and I just have to define the equation well enough to just model whatever number I started at. But here, since it'll make sense where we're going to let 0 be essentially her first year, and then 1 will be she's been with the company for 1 year. That's her second year, if you will, and so on and so forth. So we're going to start this one at 0. Just in case you're wondering why we start at 0 and not at 1, we could technically choose to start at 1, and we would just need to be careful when we're defining this back here. But we're just going to go ahead and start at 0. So when she first starts with the company, what's her salary? Well, it's $35,000. So what we're going to do is we're going to kind of build up the first couple and try to see if we can see the pattern well, you might even see the pattern already, but we're going to kind of see the pattern that's happening here to be able to write the equation. Well, then what's her salary after she's been there for 1 year? Well, it's going to be her starting salary, but then she's going to earn an extra 7%. So she's going to get 7%. So 7% as a decimal, 0.07. So she's going to get an extra 7% of that $35,000. Trust and believe we could punch that into a calculator. Oh, one thing I'm going to do to kind of set up the pattern that I'm going to do for our equation over here in a second. Notice that I've got 35,000 and I've got 35,000. So I could kind of pull that out, which would leave me with 1 plus 0.7. And this would be equal to, I feel like that should have more values than just that, but maybe I'm wrong. Let me triple check if I can find my calculator. Oh no, it does come out very nicely. Okay, never mind. I should just trust my notes. So then what about after she's worked there for 2 years? Well, essentially now it's taking this 37,450 and essentially going to tack on an extra 7% of that. So it's not always 7% of the salary she started with, but now it starts building on the salary that she's actually making in that past year. Again, if I kind of pull that equal value of the 37,450 out, still kind of end with this kind of pattern here. That's going to give me $40,071.50. So if I kept going, I'd still be finding this 1 plus 0.07 in each one of these. It would just be kind of this value out front that's changing each time. So if I thought about a way to try to write this in general, if I wanted to say, well, she starts at $35,000, so that'll be kind of my base case, the thing that has to be set in stone. And then how do I find any of the things after that? Well, I can essentially take the salary before and multiply it by this 1.007. If I just add those together and make 1.007 instead of 1 plus 0.007. I said that really, really fast. So essentially you take, and I should have made more space for this, you take the salary of the year before and multiply it by 1.07. That's kind of that pattern that we started seeing showing up. The 1.07 was going to be the same throughout. The only thing that was going to change was the salary beforehand. So essentially this is now going to be a way that I can define this recursively. So I have my base case of my 35,000, and I know that each extra year is going to be multiplied by 1.07 to get my new salary. Let me just clean this up a little bit. Let me maybe keep that circled. So
you put S n minus 1 for just for the previous year.
Yes, so the SN minus 1 is what's representing the salary that she was making in the year beforehand.
Where did you pull the 1 from?
You mean that?
Yeah, where did you get that?
Oh, where'd I actually get the 1 from? Got it. So looking at maybe this line here, I have 35,000 plus 0.07 times 35,000. Both of those things that are added have a 35,000, so I pulled it out. But if I pull a 35,000 out of here, I kind of need to keep its place. Okay. So that's why there's that 1 that kind of shows up there. So if you were to...
It gives you the amount to add the percentage raise onto.
Pretty much. So essentially, if I were to take this line and distribute that 35,000 back in, that's why I need that kind of placeholder of 1, because otherwise I wouldn't get the same thing that I started with. Too many little dots floating around here. So now say we wanted to figure out how much she was making after 5 years. Well, there's kind of 2 ways you can think about this. There's kind of a bottom up and then a top down way. So we're going to look at both. So the bottom up way would essentially be kind of what we were starting to do, where we'd have to just start from the bottom and just keep building up until we get to the point that we need to be at. That's kind of the downfall of these recursive things, is that if we want a value, we have to know everything before it. But if I wanted to do that, so we know the first few of them, but let's just write them out in generality again. So her first salary was that 35,000. And then I want to write this out in a bit of formality, if you will. So I'm going to use kind of this notation of the function that we just created. So I would want S of essentially 1 minus 1 times 1.07. So S of 0 times 1.07. So that 35,000 times 1.07. Which again, we've technically already found, but I just wrote it out in a little bit more generality with kind of these pieces in here. And then if I want to find S of 2, well, if I use my kind of function idea here, N is 2, so I have S of 2 minus 1 times 1.07. So S of 1 times 1.07. So it's 37,450 times 1.07. Which again, that one we already found. And now we finally get into ones that we didn't have yet. But it's the same kind of idea. Here we'd have S of 3 minus 1 times 1.07, so S of 2 times 1.07. So that $40,771.50 times 1.07. Trust and believe we could type these into a calculator, so I'm just giving us the values here. You can see how these are going to slowly get very tedious very fast. And we got two more. 4 minus 1 times 1.07. So S of 3 times 1.07. So that 42,000 blah, blah, blah. 1.07. So 45,877. Whoa, pen started freaking out. And 89 cents. And then S of 5 minus 1 times 1.07. So S of 4 times 1.07. So 45,877.89 times 1.07. So we finally now know that she's been working there for 5 years. After 5 years, she will make $49,089.32. I'll pause for a second. I know I wrote some of those down really quickly, but they same pattern. So hopefully after a little while it started to click, but let me know if there are questions, of course. Yep.
Necessary format to write it? Really
I'm trying to think about, no wait, I haven't assigned any chapter 3 web assign, no wonder I don't know what it looks like. Brain working, how words. It was asked if we have to write it out in this kind of formality because, you know, it gets highly tedious. I would say for an exam or a quiz, probably the first one, but then after that, just go ahead and start multiplying things by 1.07 and call it a day. The reason I was hesitating so much is because sometimes WebAssign can make you write things out in a lot of generality. I haven't assigned any of this for WebAssign, so I don't know what they look like yet. But it's possible that they might have a bunch of blanks and you need to kind of fill it all in. So that was kind of the bottom up way. You start from the bottom value and you build up to the value that you want. We're going to do it again in what we call the top down way. So essentially this starts with what you want and you build it down until you get down to the thing that you actually know and then kind of collapse it all in on itself. You'll see what I mean in a second. So, and you would never have to do both of these for like one question. You kind of pick whichever one is your favorite and call it a day. But on this, essentially what you do is, well, S of 5, well, that would be essentially S of, why do I keep writing N? 4 minus 5 minus 1, I'm getting ahead of myself, times 1.07. So S of 4 times 1.07. Now I'm going to stop writing the N minus 1 case, and I'm just going to skip to the actual number. So I'm going to just skip to like S of 3 and S of 2 instead of, because then I'll just run out of space. But essentially then, what I can do is I can take this, and I can write that as S of 3 times 1.07. But then I still have that extra 1.07. So let me get some colors up in here. So S of 4 becomes this S of 3 times 1.07. And then it essentially keeps going down until you get to the thing that you actually know the value of. So we could keep rewriting that S of whatever. So S of 3 would become S of 2 times 1.07. But then we still have those two 1.07s that were still there. So this kind of breaks up into that piece. S of 2 would become S of 1 times 1.07 times the three 1.07s that were already there. this S of 1 becomes S of 0 times 1.07 times those 4 1.07s that were already there. Is that enough? That one, 1, 2, 3, yeah. Why do I? Oh, okay. Now, if you want, you can also rewrite this a tiny bit more and just group all those 1.07s together and just say 1.07 to the 5th. And then you could punch that into a calculator. Well, sorry, I should have replaced S of 0 with what it is before you punch it into a calculator. So S of 0 was 35,000. Now this is going to give you $49,089.31. Up the tiniest bit, please. Which is 1 cent off from what we found in the other one. That's just a rounding error kind of deal. There's, as you can tell, they're so obnoxiously close that it shouldn't throw you off at all. That's just a rounding thing. So those are kind of your two choices when we have to find these values for these recurrence relations. You can either start at the bottom and build up, or you can kind of start at the top and break it down until you get to the value that you know. Tedious in both directions. I know. So hold on. Everyone seems to be done scribbling. What up?
Well, the power is the number of years, right? Pretty much. So
In this case, yeah. So first off, teams, the question was, do we kind of have to keep writing these kind of intermediate terms, or can you jump kind of from one to the bottom if you kind of see how it's going to lay out? So in this case, we do have that 5 kind of comes from the number of years, just because that's the pattern we have going on. Sometimes we'll have more complicated ones. But in terms of this one, since it's quote unquote simple enough, and I just mean it's 1.07 times the thing before it, if you can kind of tell in your mind where it's going to go ahead and jump from one to the other. I want to be careful with that, though. I will say that, like, on a quiz or exam, the more work you show, the more partial credit I can give you. So, like, if you were to jump from one to the other and just get it plain old wrong, I'm not sure where you went wrong, so there's not going to be a lot of options. But if you think that you got it you got it down, and you want to just jump to the 35, I would at least write S of 0, 1.07 to the 5th before replacing it with the S of 0 value. But I think that would be all right. Okay.
So you could also use this to say, could calculate like how you could figure out how long it would take if you put like a number, say how many years would it take to get to this wage. You could put that on the other side of the.
Yeah, and then you'd have to use logarithms to solve it, but you could totally do that. Yeah, you could totally.
Like natural log, and then you could move the.
Yeah.
In front.
Yeah, you could totally say at what point is she going to start making $55,000 and use logs to solve for that kind of power here that you would need. You could do that.
One example of whatever I've figured out what might actually be.
Use logs. Yeah. All right. So note that a recurrence relation must have a non-recursive base case. So we needed that starting point of $35,000 for this case. There always has to be a set in stone thing that doesn't rely on something else. You need a starting spot, or else you're just going around in loops till you die. All right. Let's look at the Fibonacci sequence. Sequence very near and dear to my heart. So, Leonardo Pisano, I never knew his middle name. Fibonacci kind of had this problem that he was thinking about, where you got some rabbits, and you put them in a little pen so they can't get out. And he put a pair of rabbits to begin, and he wants to essentially know how many pairs of rabbits will be produced from that pair of rabbit in a year. If it's supposed to be that every month each pair is going to beget, that's a fancy word, a new pair from which the second month on becomes productive. So essentially, if they're in there for 2 months, suddenly there's a new pair of rabbits. And if you leave that pair of rabbits in for 2 months, all of a sudden there's a new pair of rabbits from that pair of rabbits, but the other pair of rabbits was still making new rabbits. You know, so we're going to have these rabbits. And so we want to consider the fact that these are magic bunnies that never die. And n is the number of months that have gone by. And we want to know how many pairs of rabbits we have after n months. So we're not counting the actual number of rabbits, we're counting the number of pairs of rabbits. And we're going to assume that the first pair still also takes kind of that 2 months before they start having babies. So I want to look at this and I want to figure out how many pairs of bunnies we got. So I am not an artist. So let's just take my little bunnies. It's my bunnies. So we have 1 pair of bunnies to begin. So after the first month, there's just still the 2 bunnies. During the second month, it takes 2 months before they have babies. So the second month, it's still just that first original pair of bunnies. Excuse you. Zoom back out. So we still only have 1 pair of bunnies. But now that they've been in there for 2 months, they finally have another pair of bunnies. Now we got 2 pair of bunnies. Well, now, this original pair of bunnies is now just going to keep making bunnies forever. But this pair of bunnies needs to wait 2 months before they're going to have bunnies. So, in the next month, we have the original pair of bunnies. We have their original babies. But now there's another pair of bunnies. Now there's 3 pairs of bunnies. Well, now, since it's been 2 months since these bunnies have been around, they finally start making bunnies too. So in the next month, we'd have the original pair of bunnies, their original babies, their second pair of babies. But again, now that it's been past 2 months for them, they can just keep making babies till they die, which they don't because they're magic bunnies. So we got a 3rd pair of bunnies from them. And then that original set of babies actually starts making babies too. So now we got 1, 2, 3, 4, 5 pairs of bunnies. And it's going to keep getting more and more obnoxious as you go. Because now the green ones would start making bunnies, and then the month after the red ones would start making bunnies. There's too many bunnies. What up? Nope. I very much assume not. Remember, these are magic bunnies. These aren't real bunnies.
They can never die.
These are magic special bunnies. This was a terrible experiment. We're going to be overrun with bunnies. But essentially, that's, kind of essentially what the Fibonacci sequence does. So if you think about this and the pattern, so since these poor little bunnies never die, every month we're going to have the same amount of bunnies that we had before. So the same amount of pairs in the previous month. But then we're going to have on these extra set of new pairs, right? So you never lose the amount that you had before. They're just going to stick around forever. I hope your pen is very, very large. But since it takes 2 months before the pairs reproduce, then the number of new pairs is the numbers of pairs present 2 months before. So essentially the Fibonacci sequence is defined in the following way, because this does model the Fibonacci sequence. Fibonacci sequence, if you don't know, starts with 1 for the first 2 terms. So for n equals 1 and n equals 2, the Fibonacci sequence is 1. And then once again, I should have put some more space in between here, but we have essentially the one before plus the 1, 2 before. And you add them together, and that gives you your next. Let me zoom in on that because I ran out of space. So I'll zoom in and maybe it'll make it easier to read. So essentially, now I gotta zoom back out. The first terms of the Fibonacci sequence: 1, 1, 2, 3, 5, 8, 13, 21. So essentially the first two are set, and then essentially take the last two terms and add them together to get your next term. So that's why the first two kind of have to be set. So 1 and 1 are set, but then 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, blah, 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 so on and so forth. The Fibonacci sequence actually comes up a lot in nature. Dang, I read what they were and now I've forgotten what they are. I know they come up, I believe, in sunflower seeds. It's kind of weird when the sunflower seeds grow up. It's like in a Fibonacci sequence. And I know some flowers kind of follow a Fibonacci spiral. It's actually really, really cool if you look it up.
It was F is n minus 1 plus F is what?
Fn minus 2. And I should have put some more space in there so I could have actually written not nice. But there's, yeah, actually a lot of spaces in nature where the Fibonacci sequence shows up, which is just really, really cool to me. But anyway, so yeah, that's the Fibonacci sequence. Now to kind of do something completely different. So that was just kind of an extra example of something we can define recursively. So we can define the Fibonacci sequence recursively. We also have this thing called factorials that we can define recursively as well. So the factorial function is defined as, now we use kind of an exclamation point here, which is super fun because it just looks like the variable's yelling. So we have n factorial would essentially be equal to n times n minus 1 times n minus 2 times blah, 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 till you get to times 2 times 1. So essentially you take all the numbers from n to 1 and multiply them all together. So this would be for non-negative integers, so you can't find a factorial of negative. And by convention, we say that 0 factorial is 1. That's just something that we all agree to be a thing. So we can essentially define this recursively. So I'm going to leave some space here for the recursive thing that I'm going to write in a second. But if you think about it, so 1 factorial is essentially 1 factorial, sorry. 1 times 0 factorial, because 0 factorial is 1, so 1 times 1 is 1. And 2 factorial, well, this should be 2 times 1. So you can also think about that as 2 times 1 factorial. I'm kind of building up to the idea of what the factorial is going to look like, the recursive definition is going to look like. If you have 3 factorial, well, that should be 3 times 2 times 1. But 2 times 1 is 2 factorial. So I could write this as 3 times 2 factorial. And so on and so forth. So I can always kind of define this factorial in terms of the one before it. So if I wanted to define n factorial, I could do so recursively by saying that it's equal to 1 when we're at 0. That's the one that we all just kind of agreed to be a thing. And then for each later one, I can essentially take that number and multiply it by whatever the factorial of the previous number is. So for n greater than 0, we can kind of use that idea that was kind of built up down here. Let me write one more out just in case. So 4 factorial would have been 4 times 3 times 2 times 1. But 3 times 2 times 1 is exactly what 3 factorial was. So even though you can kind of also think about it non-recursively, you can literally just think of it as multiplying all the numbers from that number down to 1. But it can also be defined recursively in this way.
So it was just decided that the 0 factorial is 1.
So people just said, let's agree that 0 factorial is 1. I feel like I used to know the actual full reason. I think it has to do with when you do binomial code. No. There's some stuff you do eventually where you want to divide by some factorials, and you would want to, I forget. I used to know the exact full reason as to why 0 factorial is equal to 1. But it's just essentially, we need it to be that way, or else things that should work don't work. That sounds weird, but it's like some math later on that we know should be able to be done would not be able to be done if we don't allow 0 factorial to be 1. So we've just kind of all agreed that that's just going to be a thing. I can look that up if you want. I used to know it. Forgotten it. Last thing in here. Yeah, last thing in this section is going back to binary trees a little bit. So of course we just talked about that the other day. That was on your warm-up. So in general, a binary tree is a tree where each vertex, which I could also call a node, so if you see the word node, it's also talking about vertexes, has at most 2 children. So remember, you could only have 2 children from each kind of vertex. You couldn't have 3 children. That's why it was a binary search tree. So a vertex with no children, I kind of said this earlier without having properly defined it, is a leaf. So kind of the things at the very bottom of the tree are called the leaves. The leaves. Leaves? Leaves. The depth, which we will abbreviate as D of V, of a vertex V is the number of edges in a path from the root to that vertex. So if you start at the very top, how many edges do you have to pass through to get to that vertex you want to talk about? That's going to be the depth of that vertex. The height of a binary tree is the maximum value of these depths. What is the largest depth you have in that binary tree? Or in a, well, tree in general, but specifically in our case, binary trees. A binary tree is called complete if every leaf has the same depth. Every leaf has the same depth. And we're going to just call that N. And every non-leaf has 2 children. It's kind of, the binary tree is as full as it can be, and it kind of, there are leaves, all of the leaves have the same depth, and essentially it's filled out completely in the middle. So you don't kind of have, so say you start here and you went over here, you went here, and then you went here, and here, and here. So this would be non-complete. Let me just write that down so there's no fusion. Complete. So every leaf has the same depth. So leaves have same. I did it again. Leaves. But the problem with this one is that we have this non-leaf up here that doesn't have a second child. So that's kind of what it means, is that it's kind of filled out as much as it can be. And then all of the leaves are kind of at that same level. So if you don't have those 2 things happening, it's not complete. So we're going to do one tiny thing with that. We're going to consider this. So this would be a complete tree. Everything has 2 children except the leaves, because that's where we stop. And all of the leaves are essentially at the same depth. In this case, our depth would be 1, 2, 3, and 4. Essentially, in any case, I chose an arbitrary path. But any leaf you decide to go to, you'd have to pass through 4 edges. So note that this is a complete binary tree with height 4. Because again, absolutely any path between the root and a leaf, you'd have to pass through 4 edges. So what if we wanted to find a recurrence relation to give the number of vertices in a complete binary tree of height n? I want to try to zoom out a little bit because I want to keep this tree in here while I write some other things on here. So note, in this binary tree, what color do I want to use? Let's use this one. There are kind of two tinier complete trees. And within those ones, there's also two other tinier trees and tinier and blah, 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 and keep going. That's kind of the thing we're going to use since we have that pattern. It's kind of essentially taking two complete trees and then just connecting them together to a root. That's how we're going to be able to find this recursively. So let me kind of write that down. So note that a complete tree contains two smaller complete trees. And let's just name them T sub 1 and T sub 2, just so that we can use them later. And essentially, the difference between those two tinier trees and the original tree is that they're joined at a root. That T sub 1 and T sub 2, the two tinier trees, what's their height? Well, they have a height of essentially the original thing minus 1, so they have a height of 3 in this case. Because you're essentially just getting rid of that one edge that connected it to the root. I don't really want to go past that tree, but I kind of have to. This is true in general. Kind of babbling a little bit, but so a complete binary tree, if I want to write this out kind of in generality, so a complete binary tree of height n will have two smaller trees of height n minus 1. So essentially that idea is going to allow us to define this recursive relation for how many vertices we're going to have. So hold on a second before I write down whoop. Let's try to leave most of that in there. So say I want to define this recursive relation for the number of vertices. Is there another I in there? I don't think so. And we're going to say that the height is that n value, so that's what we're kind of using to find these. Well, what's the smallest height you could have for a tree? Technically 1. You know, it's literally just a dot. That's technically a tree. It sounds stupid. It's a stupid tree, but it's a tree. It follows the definition of a tree. So we could have, and now that the height of that would technically be 0. Because how many edges do you have to go to get from one vertex to another? None. There's only one vertex. And let me just write a leaf next to it so we remember if we're looking at this later that while it sounds silly, you can just technically have a singular leaf as a tree. How many vertices would be in that tree? Just the one. So essentially, how would we build another complete tree from that? We would essentially take that tree, duplicate it, because again, a complete tree is made up of two smaller trees. So we would have to duplicate that tree we have and then join it to a root. So if you think about how many vertices that would mean we would have, is we would have twice the amount of vertices of the tree that we were just talking about, because you have to duplicate it because we need this to be complete. And then we have to connect it to a root. Well, that root is an extra vertice. So we tack on one more. And that will be true for anything that's greater than 0, any height that's going to be greater than 0. So let me try to write down the reasonings for these in case people are looking at this later or just haven't got it yet. So we have the two smaller trees. And this is going to be the root that joins them. So this is just a way that we have now just defined an essentially a recursive relation for finding the number of vertices on absolutely any complete binary tree. Because of the fact that we recognized, if I can zoom out a little bit, zoom. Now I gotta clean up the little things that I put up there. I'll scroll back down in a second. So the first thing we recognized was that essentially these trees are made up of two smaller trees. So if we essentially keep breaking it down into two smaller, two smaller, two smaller, two smaller until we're at just a leaf, that's how we kind of defined that recursive definition. We're able to start at the leaf and then we're able to build it back up by essentially taking two leaves and connecting them together, and then two of those trees and connecting them together, and so on and so forth until you're done, kind of idea. So that's what this is exactly saying. Questions, concerns on that? Yep. So that n-1 is in those parentheses to be v of n-1, and the plus 1 is tacked on at the end. So like this thing, now I've stopped drawing. This thing is one thing. So you can't take that -1 and add it with the +1 and cancel out, because that it has to be part of the v thing, if you will. Any more questions? All right. Technically a little bit sooner than I would usually do a quiz, but it's not worth going into anything new, so let me get y'all off the big screen because y'all should put your cameras up, but then I've got to make